So we are going to start with the computation of finding of limits at infinity. So limits at infinity. So remember, we use this sign to represent this sign shows infinity, and it's just a symbol or a sign that is used to represent a very, very large number. So infinity so this is how we write infinity sign, and it's simply a sign used to represent a very, very large number. Positive number. It is not a number on its own. And then when you write minus, then you write the sign, means minus infinity or negative infinity. So this is a sign used to represent a very, very large negative number. It is not a number on its own. So that means that when you say, so expressions of the form infinity minus infinity, or infinity minus infinity plus infinity, or saying infinity power 0, saying 0 power 0, 0 over 0, are called intermediate forms. So when you say infinity minus infinity is not 0, infinity plus infinity, infinity power 0, 0 power 0, 0 over 0, those things are called intermediate forms. And as we previously saw in the last section, the case of 0 over 0, that thing is not defined. So for you to calculate limits for quotient of functions, which on direct substitution gives you 0 over 0, you know that you have either to do factorization or rationalization to remove that intermediate form. So we've been tested now to compute. So the goal of this section, to compute the limits whose values involves either plus or minus infinity, i.e., we want to see how to compute a limit of the form limit as x approaches plus or minus infinity of a function f of x. So these are the kind of questions we are going to be dealing with. How do you calculate limits where the x value is approaching either plus or minus infinity? So let's explain some notation before even we narrow down into the nitty-gritties of the limits themselves. So the notation when I write this statement means x increases without bounds. And the notation means x decreases without bounds. So this is what I mean. I remember when we were discussing about real numbers, we say that real numbers are numbers which forms this line. So to the left, we have negative infinity. To the right, we have positive infinity. So when I write this statement, x tends to infinity, means that x value is increasing without bounds. So they are making the value of x to grow large and large and large and large as possible. While this notation, x tending to negative infinity, means you are making x to decrease without bounds, or simply you are making the value of x larger but in the negative direction as much as you can. So we will write this to mean so to compute limit as x approaches plus or minus infinity of f of x when f of x can be written in this form, where q of x is non-zero, p and q are polynomials, we simply pick the x with the highest power in q of x, that means denominator, divide this with each term both in p of x and q of x, then apply limit loss. So if the function is in the form of p over q, then where both p and q are polynomials, you'll go to the denominator, identify the x with the highest power, then pick that x with that power, divide by each term both in the numerator and denominator, and then finally compute the limit using limit loss. I remember we have said positive infinity means a very, very large number. Negative infinity means a very, very large negative number. So positive infinity, very large positive, negative infinity, very. So the question will be, if f of x is not in the form of p over q, how do you deal with it? So that one, you just deal with the question directly. For example, so the case whereby the function is not in this form, if it's just say a polynomial but it's not a rational function, then you interpret the problem just from the definition of x tending to positive infinity, meaning that x is growing larger without bounds in the positive direction. And if it's negative infinity, that means x is going to be growing larger without bounds in the negative direction. So this note that we are giving here is simply applicable to the limits whereby x is approaching plus or minus infinity, and p and the function is written as a quotient of two polynomials. So let's say, for instance, if we are asked to compute limit as x approaches infinity of x, what will be the value? So when you do direct substitution, that means that the value of the limit becomes so what happens to x as x grows larger? What happens? Yes. So when x grows larger, also the value of the function, which is x, also grows larger. So the value of this will be just positive infinity. That's by direct substitution. Now, if you have limit as x approaches infinity of x power 2, what will this be? still be infinite, because remember, so when you make x larger and then you square that value, you even get a very large number, okay? Yeah, so it's like we are saying infinity, which is a very large number, then you square, you also get a very large number. So still the value is positive infinity. Now, what will be the limit as x grows larger, but in the negative direction of x squared? Positive infinity, because it's like if you do direct substitution, you have negative, very large number, then you're squaring it. So you're going to get a positive number. So negative infinity. And what will happen if you find limit as x grows larger and you raise x to power n? Given that n is positive. Positive infinity still. So the value will be still large. And what will be the limit as x approaches infinity of 1 over x? So this is how we interpret it. So remember, we have agreed that infinity is not a number. It's just a simple list to show a very, very large number. Now, what do you get when you make the denominator large, keeping the numerator fixed to 1? Now, so let's, for example, let's do this. If you say 1 over 10, you get 0.1. If you say now, let's increase the denominator, 1 over 100, 0.01. Let's make the denominator larger, 1,000. 1, okay? So let's also make that value larger. So say 10,000. 0.1, okay? And then let's say make it 1,000,000. Because remember, x approaching infinity means that the value of the x is increasing. So we want to see the trend on what kind of result we get as we increase the value of x. What can you say? As you make that x larger, the value of the fraction becomes? That's true. The value of the fraction becomes small, okay? Yeah. So that small value is roughly, if you are to do rounding off, you remember the way we started by introducing limits, how we're getting limits by using table. So remember, the trend is that this way we are converging. So we are going down. So as we continue going down, we are roughly approaching or converging to each number. Yeah, so you see, you can even just draw a small number line. So this number line, say this is 0, and this way you have 1, and say this way you have -1. So for example, 0.1 will be somewhere here. So the next value, 0.01, you are sure that it will be towards this side, okay? Yeah, and even the next one will be closer towards this number here, okay? So as the value of denominator becomes larger, the fraction becomes very, very small, close to 0. So therefore, limit as x approaches infinity of 1 over x is 0. And what would be the limit as x approaches negative infinity of 1 over x? So as you make x to be negative, but then you're increasing the negative values of x. It's the same thing as just using this, making this negative. So the only differentiation will be negative signs will be here. Where will it be converging to? Yes, to be still the same thing, because remember, if this way you have negative 0.1, then you are sure that negative 0.01 will be closer to 0, that will be to the right of this side, okay? So it'll be moving towards the 0 here. So this will still be 0. And what will be the limit as x approaches infinity of 1 over x squared? It will still be 0, because remember, if we have said that 1 over x will give us 0, so when you increase the value of x, then if you make x larger and you're squaring it, you're also getting even a larger number, okay? So when you divide 1 by a very large number, you are going to get a very, very small thing, so which is close to 0. So limit as x approaches infinity of 1 over x squared. And what will be the limit as x approaches in a negative infinity of 1 over x squared? Will still be 0. Because as you square the denominator, you are making it larger than 1 over large number still to 0. And what would be the limit as x approaches infinity of 1 over x power n, where n is still greater than 0? Still 0, correct. And what will happen if you are getting limits as x approaches infinity of e raised power x? Positive infinity, because as you make the power of e to be a large number, the overall effect is also you are making the value of the exponent to be the value of the whole function to be large, okay? Yeah, so this will be positive infinity. And what if we have limit as x approaches infinity of 1 over e raised power x? Zero, because you are making the power of e to be large number. So the overall effect is that you are going to get a very large number in the denominator every time you increase the value of x, and 1 divided by a very large number is simply 0, okay? So that's how we interpret it. Now, let's see examples. Yes? Yeah, so for instance, if we have this, that's a good question. If you are giving limits as x approaches negative infinity of x as a number. So I'm asking you, what is the value? How does the value of x behave when you make x to be large in the negative direction? So this is the number line. This is a negative infinity. So say this way is 0, this positive infinity. So what happens to our general value x on this line as you make x to move toward the negative direction? It's like you're just doing direct substitution. So where there's x, you're putting negative infinity. Okay? And if I give you limit as x approaches minus infinity of x power 3, it's the same thing is like we are just doing direct substitution. So you know that when the power is odd, then if you have a negative sign, then the negative sign will be still be in the answer. Okay? Yeah, so this cases we get. So you can in fact generalize it and say limit as x approaches minus infinity of x power n will give you two values, positive infinity when n is even and negative infinity when n is odd. So let's see now cases whereby we have rational functions. Okay, maybe let me give now other. Let us do more examples. So evaluate limit as x approaches infinity of 2x power 11 minus 5x squared, x power 6 plus 3x squared plus 1. So write that question. Yes, x, the power of x is 11 in the first term, okay? Good. So the key thing, our solution, recall that we have said limit as x approaches positive infinity of 1 over x power n is always a 0, correct? So you try to rewrite this. If we have more than two terms in a given expression, then you try to write it in such a way that you are going to have some fractions which involve x as being the denominator. So we'll say limit as x approaches infinity. So what is the highest power of x in that expression? 11. So we write it as x power 11. Okay, let me just rewrite the equation. 2 and then minus 5x power 6 plus 3x squared plus 1. So you write this one as limit as x approaches infinity. So you factor out that highest power. So when I factor out x power 11, how would be the first term in this expression? Two, correct? Minus 5 over x power. Yeah, so that at the end of the day, when you multiply, we get power 6, okay? Yeah, and then that's why you have always to find a way of connecting these things we learn from one unit to another unit. These are just first of cases we do in Math 20. Now, so it will be 3 over which x raised power 9. So that at the end of the day, we get power 2. And then plus 1 over x power 0. Remember, when you expand the bracket, you get back the original expression. If you put a 0 and you expand, I assure you are going to get 1. Remember, x power 11 is affecting everything that we are writing in the brackets. The question is that which power should I put here so that when I multiply 1 over that x power multiplied by x power 11, I get 1. If you are able to interpret these first 3 terms, you should not have problem to explain the last one. In fact, these first 3 terms were more technical than the last one. It is harder to get these answers we have obtained than the last term. So when, okay, let's work by what you are saying, and then you'll see why it is wrong. Yeah, so that now we get the correct answer. You know the correct answer, the difference is that the way you're explaining it is the opposite, but you have the idea on what you're supposed to do. You know that x power 0 is always 1, okay? So if I put 11 here, do you see that at the end of the day, when I multiply, I still get 1? Yeah, okay? Yeah. So then now, as x approaches infinity, limit, okay, let me not say, let me not repeat myself. So as x approaches infinity, what is the value of as x approaches infinity, 2 approaches which number? And 5 over 11, x power 5 approaches which value? Two approaches? Okay, maybe we. So let's just. So it's like we can apply product tool for limits. Okay. This bracket and this x power 11. So this is the same as limit as x approaches infinity of x power 11 times limit as x approaches infinity of 2 minus 5x power 5 plus 3x power 9 plus 1 over x power 11. I hope that will make sense to you from what you have discussed earlier on. So if you have product of 2 functions, if you're getting the limit, you get product of the limits, okay? Yeah. So what is the limit as x approaches infinity of x? This is the infinity product. And then times. So we can say we put in the limit. So limit as x approaches infinity of 2 minus 5 limit as x approaches infinity of 1 over x power 5 plus 3 limit as x approaches infinity of 1 over x power 9 plus limit as x approaches infinity of 1 over x power 11. Do you see the sense in that from this previous step to what I'm writing? Huh? From the properties of limit. Huh? Yeah. So tell me, what is the value of the limit in the first? What is the limit in the first term in the bracket? Why? Why infinite? Don't forget what we said. So do you see an x here? Yeah, so remember that rule still applies, that whenever you are getting limit of a constant in the same constant, doesn't matter where the x is approaching to. Yeah, so regardless of where x is approaching, these are constant. So limit of a constant is a constant. So this will be 2. And then, yeah, because this one, you know that this will be 0, okay? And next. Yes, this limit is also going to be 0. This one, this is also going to be 0. So it's like we have infinity times 2 minus 5 times 0 plus 3 times 0 plus 0, which is just infinity times, this bracket will give us 2, okay? So final, if you have a very large number and you multiply by 2, what is the nature of the result? The base. Okay, like pick like a trillion, multiply by 2, you get 2 trillions. So is it a big number or a small number? It's a big number. So if you have a big number, you multiply by a positive number, you get even a bigger number. So the answer still remains to be infinity. Okay? Yeah. So that's what that question gives. Okay, big. Yeah, okay. Okay, fine. But okay, maybe we can do this. In my explanation, was it making sense? I give you a question now to try at the same time. Maybe. So because I'll be sharing this after the class. Yeah, let me write for you. You can try to work it out, and then we'll discuss the answer. So this x is approaching minus infinity. Don't be scared by minus infinity, yet you have done positive infinity. The interpretation is still the same. The logic is still the same. It is negative infinity. Okay. So let's, I don't want to say whether the answer is correct or wrong. So tell me, what have you done in the first step? Okay, but then, yes, correct. So that's the first step. So factor out the highest power. Okay. So which will be 3 minus 1 of x squared, correct? X power 3, yes, minus 7, x power 4, correct. Step 1 is correct, okay? Now you say limit as x approaches minus infinity of 3x power 4 minus x squared plus x minus 7 is the same as limit as x approaches minus infinity. Now you rewrite what we have written here, x power 4 into 3 minus 1 over x squared plus 1 over x power 3 minus 7 over x power 4. Then you apply limit properties on product. Yeah. So which will give you limit as x approaches minus infinity of x power 4 times limit as x approaches minus infinity of this bracket, okay? Yeah. Okay, so what is the value of the limit here? It's like we are doing, you have negative infinity, that's the value of x, then you are raising to power 4. So if you have a negative number raised to power an even power, do you get negative or positive? Mm. Mm. Okay, so that when there's no mistake, you got a positive. Okay, no problem then. So let's go to the next step. So we'll have limit. Let's expand this. X approaches minus infinity of 3 minus limit x approaches minus infinity of 1 over x squared plus limit x approaches minus infinity of 1 over x power 3 minus limit. In fact, I can factor out 7. Hope that one doesn't confuse you. It doesn't. So then x approaches minus infinity. So what is the first limit in the bracket? Y negative 3. Y negative 3. Okay, remember the things we stated earlier on still remains. 3 is a constant. You are not seeing any x here. So when you say x is moving towards negative infinity, there is nowhere x is affecting this constant 3. 3 remains to be 3. So it's not changing, it remains to be 3. Okay? So it's not negative 3, but remains to be positive 3. It will be negative 3 if in the question itself there was a minus sign. So, yeah, so this is positive 3. And then what the limit in the second term? 0, because this will also be 0. This also be 0. So what do we get? Positive infinity. So that's what you get. Oh. Yeah. Example 3. So when you have a polynomial which doesn't involve quotient, that you try to introduce quotient in a nice way of factorization and see how the limits behave. Now, if I have the limit as x approaches infinity of 2x plus 5 over x squared minus 7x plus 3. The next problem. Do you remember what we said in case of rational functions? So the thing is that you identify x with the highest power in the denominator and then divide by each of the terms, okay? And please note that denominator is a key. What in the denominator is what matters, not what in the not any other place in the expression. Denominator, highest power in the denominator is what guides on what you're supposed to. So you write this one as limit. What is that value in the question? So x with its power that is highest in the question. X power 2. So you'll solve, you'll pick this first term, 2x, and then divide by that x power 2 plus 5, divide by the same x power 2, x power 2, divide by the same x power 2, minus 7x divided by x power 2, plus 3 over x power 2. That is step 1. Identify x with the highest power in the denominator, pick it, then divide by each term. Okay? Yeah. So the next step now, just simplify in the normal way. So this will give us limit as x approaches infinity. Now, what does 2x over x squared give us? What? Just tell me the answer. You don't. I just want to hear what you want. And actually, it's advisable if it's advisable when you have fractions and things that denominator have x, it will be easier to interpret the limits. So 2x over x squared gives you okay. So we don't have to put it negative. Let's just and the other we don't complicate the obvious. X of x squared is 2 over x. Or do you want to disagree this? Okay. Okay. Fine. Good. Denominator first term will be 1. And then minus 7 over x plus 3 over x. Good. And then here we apply the limit laws. If you have quotient, we said limit of quotient is the same as quotient of limits. You remember? So we get limit of the numerator and also limit of the denominator. So limit as x approaches infinity of 2 over x plus 5 over x squared divided by limit as x approaches infinity of 1 minus 7 over x plus 3 over x squared. That one you agree from what we did in the previous session, limit laws, okay? Yeah. So still, this will be limit as x approaches infinity of 2 over x plus limit as x approaches infinity of 5 over x squared over limit as x approaches infinity of 1 minus limit as x approaches infinity of 7 over x plus limit as x approaches infinity of 3 over x squared. Can you be trusted with those limits? Okay, so the first one in the numerator, limit as x approaches infinity of 2 over x. Remember, this can be written as, remember 2 is a constant, so you can say 2 limit as x approaches infinity of 1 over x. We get 0. So this will be 0. The second one is also going to be 0 because denominator we're making it larger. And then limit as x approaches infinity of 1. 1. Limit of a constant is a constant. The second limit, 0 is also 0 because we are dividing by x. So when you make it large, the value becomes very small. So which means we have 0 plus 0 over 1 minus 0 plus 0. So which is 0 over 1, which is 0. So that would be the answer to that problem. So next, limit as x approaches infinity. Yes, again, I'm happy. 3x squared, x cubed. George, how are you? George? Yeah, while you are waiting, let's do. Okay, good. Fine, but you have recorded, you'll be able to follow through. Good. Yeah. So 3x cubed minus 4x plus 2 over 7x cubed plus 5. Agnes, you are going now to be our teacher because now you are the one who understands these things. Guide us through. Yes. 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 Terms. Well, not the coefficient, then the x itself with its power. So the x with its power. That's the only thing that matters, not the coefficient. Okay? Yeah. So x power 3 is the highest value of x with large power. So divide in the denominator. So remember the key thing is the denominator. In the denominator, so divide each term by x power 3. So not the coefficient of the x, but the x itself and its power. Once you have studied the part terms in the denominator, the one that has size is what you actually be dividing by each term. So this is what I mean. Limit as x approaches infinity of 3x cubed minus 4x plus 2 divided by 7x cubed plus 5 for the limit as x approaches infinity. So we'll have 3x cubed, you divide by x cubed, minus 4x divided by x cubed, plus 2 over x cubed, 7x cubed over x cubed, plus 5 over x cubed. So 3x cubed over x cubed. Just 3, okay? And then 4x over x cubed. Correct. And then plus 2 over x cubed. Yeah. And then in the denominator, 7 plus 5 over x cubed. So what happens next? Yeah, using properties of limits. Huh? So limit of the numerator by limit of the denominator. So limit as x approaches infinity of 3 minus 4 over x squared plus 2 over x cubed over limit as x approaches infinity 7 plus 5 over x cubed. And then you do what you're saying. So you apply limit on each term. Huh? Yes, the first limit will be, this will be 3 because this limit of a constant, so this remains to be 3. Next. Yeah, because we can factor out 4 and then limit as x approaches infinity of 1 over x squared is 0. So this is 0. This also be 0. Seven constant. Correct. So which is simply now 3 minus 0 plus 0 over 7 plus 0, which turns out to be 3 over 7. And then next example, is that D or E? E. Yeah. So limit as x approaches infinity of 4x power 5 minus 1 over 3x cubed plus 7. Can I trust this question with you? Can you try? Yeah, try. Trust the process. Zero. George? George, are you in? Okay, so let's see. How did you start? X power? X power 3. So you have mastered the game, correct. So remember, what matters is the x in the denominator, not the numerator, okay? Yeah, that's the first thing. So divide each term by x power 3. So this is what we'll have. We'll have limit as x approaches infinity of 4x power 5 minus 1 over 3x cubed plus 7 is limit as x approaches infinity of 4x power 5 over x power 3 minus 1 over x power 3 over 3x cubed over x power 3 plus 7 over x power 3. So that's the first step, correct? You identify the highest power in the x with the highest power in the denominator. Not just anything, any x with the highest power, but with reference to denominator. That's really what matters. So limit as x approaches infinity, first term in the numerator will be 4x squared minus then over 3 plus 7 over, correct. Then in the numerator and denominator, okay? So limit as x approaches infinity of 4x squared minus 1 over x cubed over limit as x approaches infinity of 3 plus 7 over x power 3. So follow step by step so that you get all the method marks. Yeah. So limit of sum, then you can only difference, you can always get the difference of limits. So we'll have limit as x approaches infinity of 4x squared minus limit as x approaches infinity of 1 over x power 3 over limit as x approaches infinity of 3 plus limit as x approaches infinity of 7 over x power 3. So you can as well factor out 4. Okay. Yeah. X 1 over x cubed over limit as x approaches infinity of 3 plus 7 limit x approaches 1 over x power 3. So limit as x approaches infinity of x squared. Will be what do you get? Either limit of x squared as x approaches infinity. First term in the numerator, this term. So this will be 0. And then these are the limit, also 0. This limit, 3. This limit, 0. So you are sure that as x approaches infinity of x squared is 0. What's the interpretation of that? Is it true that when you make x larger, the value of x squared is 0? Is that true interpretation? Like if I have 10,000, if I square 10,000, I get 0. If I have, say, trillion, if I square, I get 0. Or I get number close to 0. When you make x larger and every time you're squaring, what is the nature of the answer that you get? You are still going to get a larger number, okay? So this is not 0, but infinity, because like you're simply replacing infinity, then you're squaring it. So squaring a large number, you still get a very large number. So 4 times infinity minus 0 over 3 plus 7 times 0. So what is 4 times infinity? If you have a very large positive number and you multiply by 4, what do you get? A very large number, you multiply it by 4. Nature of the final answer? Is still infinity. Is there still going to be a large number, George? Okay. Yeah. So this will be infinity. So infinity minus 0 still remains to be infinity. And then 3 plus 0 is just 3. So a very, very large number, if you divide by 3, what do you get? Thing which is a number which is very, very big. If you divide by 3, say 1 trillion divided by 3. What do you get? George? Is? Yes, it's still another number which is very large, okay? So, so I've given an example. I've given an example, say, if we have 99 trillion, if I divide by 3, I get 99 trillion divided by 3. Will give me which value? That 3 trillion. Is it small or is big? So the interpretation is it a big number, or small number, or 0? Sure. That 3 trillion, the example I've given, is a small number. Remember, remember, infinity is not a number. It's just a sign used to show a very, very large number. We don't know the number itself. So the 99 trillion I picked may not be the largest, so it may be more than that. So the key thing is that it's a very, very large positive number. What nature of result do we get? Is it large or small? It's still large. Yeah, so this is infinity. So the answer becomes infinity. Okay? So remember, infinity is not a number. It's a sign used to show a very, very large positive number. So even the example I'm giving, 99 trillion, may be very small. It's a number more than that. You can go beyond that 99, just using that for illustration purpose. So the key thing is to interpret the nature of the result, not the number itself, because we can't quantify how large that number is. So before we yes? Agnes, help me answer that. So George, we are discussing limits at infinity and negative infinity. So you see when this is a real line, this is what we call negative infinity, this is zero, then this is what we call positive infinity. So we are trying to interpret values of limits of functions f of x as x moves towards plus or minus infinity, either becoming large and large to the negative direction or becoming large and large to the positive direction. Okay? Good. So asymptotic behavior of a function. So if I have this is my x-axis, this is my y-axis, and I have a function say that this curve and say I have another arm here. So how does this graph behave as the value of y grows larger? How, how can you predict the way the graph will be as you extend the value, also as you make the values of y to be large and large and large? Okay, or let me paraphrase my question. As you make the value of y larger, what happens to this arm of the graph? How is the graph behaving as you extend the value of y in the positive direction? As sure. How does it continue? Does it behave like going closer or moving away? It increases, but huh? As you extend, parallel with the line. Okay, that's the observation. And what happened to the x-axis of the same curve as you try to make the value of x larger? Moving away. Okay, so it means that there's a problem in understanding the difference between moving close and moving away. So we are discussing this arm here. What happens as the value of x becomes larger? How does the graph behave? Or how does the curve behave? That's like that's the global behavior, that as you make the value of x larger, then the curve seems to be moving closer and closer to the value to the x-axis. Okay. Are you able to see that? And then what happens to this other graph, this other arm? As you make the value of x larger but to the negative direction, what happens to the curve? I'm responding to this graph here. So if I call this curve 1, this curve 2, how does it behave? As I move the value of x more to the negative side. Do we need St. Peter's to explain that? How does this arm of the graph behave as you make the values of x larger toward the negative direction, this side, this arm, this arm where I'm putting, so there are two arms. There's this what I'm calling this side 1, this side I'm calling 2. So I'm referring to the interpretation of 2. What happens as we increase the value of x toward the negative infinity? How does the graph behave? Okay, that's a hard question. If assuming that this point is say -3, and this point say is -4. If you extend this line, this graph, to where we have x equals to -4, will it be closer to that -4 or compared to where the graph is at -3, or it will be far away from -4 with respect to where it is at -3? If you make an extension of this graph in second arm. Will the graph appear to be closer to the x-axis or be far away from the x-axis at -4 and -3? Which one will be? At which point between those two numbers, -4 and -3, will the graph be appearing to be closer to the number. Which number? -4, -3. And then if you are to extend, say at -5, if you compare what is happening at -4 and -5, which point will be closer to the curve? -5, okay? Yeah, so generally from this sketch here, the graph is appearing to be getting closer and closer to the x-axis as you make the values of x more negative for this particular arm. And also this at the same time for this one, the graph is appearing to get closer and closer to the x-axis as you make the values of x larger. Yeah, it's true. So we are interpreting what we are saying. We are interpreting the curve that is given on this diagram, how it behaves as you make the values of x either more negative or more positive. Similarly, as you make the values of y more negative and more positive. But it's not touching it. So these lines with this in this given example, the x-axis, the line where the graph appears to get closer and closer as we increase the value of x to the positive infinity and to the negative infinity is called an asymptote. And similarly, with these same two curves, the y-axis is also an asymptote, which is the line that the curve appears to get closer and closer as we make the values of y larger and larger and larger. So we formally define what we call so this y will be called the vertical asymptote, while the x will be called the horizontal asymptote. So horizontal asymptote is a line y equals to k, to which the graph gets closer as x approaches positive infinity or x approaches negative infinity. So a line y equals to k, to which the graph of the function y equals to x gets closer and closer as x approaches both positive infinity and negative infinity, is called a horizontal asymptote. So to get this line, we evaluate limit of f of x as x approaches either to plus or minus infinity. And so this is what will give us the vertical. So the horizontal asymptote y is equals to the limit as x approaches plus or minus infinity of f of x, which will give you a definite value k. So vertical asymptote. Now it's also a line to which the graph of the function gets closer and closer as x approaches that line from either left or right hand side. So I'll say this is a line x equals to c, to which the graph of the function y equals to f of x gets closer and closer as x approaches c, from the right or from the left. Now to get this line, we simply equate denominator to 0 and then solve. And it should be very clear that not all functions will have both vertical and horizontal asymptotes. Even in some cases, the function may not have any of the two asymptotes. So it's not a condition that each function must have vertical asymptote and a horizontal asymptote. Some may have only a vertical asymptote. Some may have only a horizontal asymptote. Some may have neither. Ask.
How do you simplify a number of zero?
How to simplify? Do I really understand the question clearly? Are you referring to what I've written here? Okay, so probably I can explain in the example that I'm writing. Okay, so find any vertical or horizontal asymptotes of the graph So find any vertical or horizontal asymptote of the graph of the function f of x equals to 4x minus 5 over 3x plus 2. You let me know when you are ready for us to solve this. Agnes? Oh, it's problem, okay. Fine, fine. Can we solve the problem now? Okay, good. So let's start with the vertical. So vertical asymptote implies equate denominator to 0 and then solve. So in our case, denominator is 3x plus 2 equal to 0. And what do you get as x? Negative 2 over 3. So therefore, the only vertical asymptote of f of x is the line x equals to minus 2 over 3. So if you meet such a problem, actually, you should do it without struggle. So simply take the denominator equate to 0 and then solve. If the function given has no rational form or denominator can't be, there's no denominator in the expression, then there's no vertical asymptote. If this structure of the function is f of x given by, say, p over q, so take q to 0 and then solve the question. Ask. Yes. So remember this, like what I was doing in this diagram. So like in this case, the y-axis is what we are calling the vertical asymptote. So it's a line where the function appears to be getting closer as x approaches. It's a line of this form, x equals to c. I remember this is the exercise we did in March. Was it March 125? How we write equations of either vertical or horizontal lines. So it's a line of this form where the function appears to be approaching as x tends to get closer and closer to this value c. We wrote this is a constant, yes. What did we write? Recheck your work. So just recheck. If you copy the correct thing, then you have the correct answer. So for horizontal asymptote, how do we find it? From the definition? That's an George, that's an interesting way. Yeah, it's expected. It's expected. Your answer is wrong, but good for learning purpose. Okay, horizontal asymptote, you don't know. So remember, vertical is only where you use denominator. Horizontal, we get limit of the function as x approaches plus or minus infinity. This is what you wrote. This is what you wrote for the case of vertical asymptotes. So you simply get the limit as x approaches plus or minus infinity of that function. Okay? Yeah. So we are going to get a limit as x approaches plus or minus infinity of f of x. And then this is what will give us y. So remember, these things we did in Math 125, that any vertical line is given by the equation x equals to a constant c, and any horizontal line is given by y equals to number k. So these are not new things. We have already discussed them in a different course. So this is vertical line, and this is horizontal line. So we'll have limits. So y equals to limit as x approaches plus or minus. Our f of x is 4x minus 5 over 3x plus 2. Infinity, plus or minus infinity. Yes, work out and tell me the limit. So remember, this will be y equals to, so we are dividing each term by which number, which variable? X, because that the x in the denominator is only 2 power 1. So it'll be limit as x approaches plus or minus infinity of 4x over x minus 5 over x divided by 3x over x plus 2 over x. So we'll have 4 minus 5 over x over 3 plus 2 over x. Please tell me the answer to that limit. Volve? This is explained at the start of the class, so probably you will have to go and check. That's the explanation we gave before we started computing limits at infinity and infinity. So when you want to evaluate any limit involving either plus infinity or minus infinity, and you have a rational function p over q, you simply identify x with the highest power in the denominator and then divide by each of the terms, both in the numerator and the numerator. It's like the rule of the game when you want to evaluate such kind of limits. Yeah. And what matters is what is in the denominator. X with the highest power that is found in the denominator. The reference point is the denominator, not any other place, but the denominator. Yes. So in the denominator, there's only x power 1. So that's what you're taking to divide by each term. If it was power 2, then you'd also divide everything by 2, x power 2. So the final answer would be 4/3, okay? Yeah, so therefore that is the horizontal asymptote. So a small break of 5 minutes